Pour water from a glass, and it slips away almost instantly. Pour honey or syrup, and it stretches, clings, and seems to argue with gravity. That everyday difference is viscosity. Informally, we call it thickness, but scientifically it is much more precise. Viscosity describes how strongly a fluid resists internal motion when one part of it tries to slide past another. It is not just about whether something feels sticky. It is about the force needed to keep layers of a fluid moving at different speeds. Every real fluid, from air to engine oil to molten rock, has some viscosity. Without it, fluids would move in a perfectly frictionless way. But in the real world, fluids always push back. To understand viscosity, imagine a fluid not as one smooth object, but as many tiny neighboring parcels. When a fluid flows, those parcels often move at different speeds. One layer may slide quickly, while the layer next to it lags behind. Viscosity is the internal resistance that appears between those layers. In continuum mechanics, this resistance is described as stress inside the fluid. The important idea is relative motion. Viscosity matters when adjacent parts of a fluid are trying to move past each other. If all parts move together at exactly the same speed, there would be no internal sliding to resist. But once speed varies from place to place, viscosity becomes unavoidable. The technical relationship behind viscosity connects stress to strain rate. Strain is deformation, and strain rate means how fast that deformation is happening. In a simple shear flow, the fluid is being distorted because one layer moves relative to another. For many common fluids, the resisting stress is directly proportional to how quickly the fluid is being sheared. Double the rate of deformation, and the resisting stress doubles. The constant of proportionality is the viscosity. This is why viscosity can be measured as force times time divided by area. In SI units, that becomes Pascal seconds, or equivalently Newton seconds per square meter. The unit looks abstract, but it encodes a simple question: how much force is needed to make a fluid deform at a certain rate? Viscosity has different microscopic causes in liquids and gases. In liquids, molecules are close together, so cohesive forces matter. Neighboring molecules attract one another, and that attraction resists motion when one part of the liquid is pulled past another. That is why many liquids feel thicker when their molecules interact strongly. In gases, molecules are much farther apart, so cohesion is usually less important. Instead, viscosity comes mainly from collisions. Fast-moving gas molecules carry momentum from one layer to another as they bounce around. Those collisions transfer motion across the gas and create internal resistance. So both liquids and gases are viscous, but they produce that resistance in different ways. A useful way to see viscosity in action is to picture fluid flowing through a tube. The fluid near the wall does not glide freely. Because of the no-slip condition, the relative speed between the fluid and the tube wall is essentially zero right at the boundary. The wall slows nearby fluid, while fluid closer to the center is less affected. The result is a speed profile, slowest near the walls, fastest near the center line. This is why flow in a pipe is not like a solid plug sliding forward. It is more like nested layers, each moving at a different speed. Viscosity is what couples those layers together and creates friction between them. Because viscosity resists motion, a flow usually needs a driving force to keep going. In a pipe, that force often comes from pressure difference, higher pressure at one end, lower pressure at the other. The pressure push must overcome the internal friction created as fluid layers slide past each other. If the same amount of fluid must pass through the tube every second, a more viscous fluid requires a stronger pressure difference. Water can move through a narrow tube relatively easily. Syrup, oil, or glycerin may need far more pressure for the same flow rate. This principle matters in plumbing, blood circulation, chemical processing, lubrication, and countless engineering systems. Temperature can change viscosity dramatically, especially in liquids. Warm honey pours more easily than cold honey because heating gives molecules more energy and weakens the practical effect of cohesive resistance. Many oils behave the same way. Cold oil is sluggish, while warm oil flows readily. Gases often behave differently. As gas temperature rises, molecular motion increases, and momentum transfer through collisions can increase viscosity. Pressure can also matter, though in many everyday cases its effect is smaller than temperature. The key lesson is that viscosity is not always a fixed label attached to a substance. It depends on the state of the fluid and the conditions under which it is moving. Many familiar fluids are modeled as Newtonian fluids. In a Newtonian fluid, viscosity does not significantly change when the rate of deformation changes. Water, air, and many simple oils behave approximately this way under ordinary conditions. If you stir water slowly or quickly, its resistance follows the same basic proportional rule. Stress increases with shear rate, but the viscosity itself remains roughly constant. This makes Newtonian fluids mathematically convenient and very important in engineering. But the word Newtonian is not a guarantee of simplicity in every situation. It simply means the fluid's internal resistance follows a linear relationship between shear stress and strain rate over the range being considered. Not all fluids obey that simple rule. Non-Newtonian fluids change their apparent viscosity depending on how they are deformed, or how long they are deformed. Some are pseudoplastic, meaning they become less viscous when sheared. Paint is a common example. It can flow more easily while being brushed, then stay in place after application. Some are dilatant, meaning they become thicker when stressed. A mixture of cornstarch and water can feel liquid when handled gently but become resistant under sudden impact. Plastic fluids may not flow at all until a certain stress threshold is exceeded. These materials show that viscosity is often a behavior, not just a single number. There are also time-dependent non-Newtonian fluids. Thixotropic fluids become less viscous the longer they are sheared. Certain gels, paints, and drilling fluids can behave this way, becoming easier to move after continued agitation. Rheopectic fluids do the opposite. They become more viscous over time under shear, though they are less common. This time dependence matters because a quick measurement may not reveal how the fluid behaves during real use. A material might resist motion at first, then loosen after mixing, pumping, or vibration. Engineers and scientists study these behaviors through rheology, the science of how materials flow and deform under force. The idea of zero viscosity is tempting, because it suggests a fluid that flows forever without internal friction. But ordinary fluids never reach that state. The second law of thermodynamics requires real fluids to have positive viscosity, meaning they dissipate energy as motion is converted into heat. In theoretical calculations, scientists sometimes use an ideal or inviscid fluid with no viscosity, because it simplifies the equations and helps isolate other effects. But it is an approximation, not an everyday reality. The major exception is superfluidity, a quantum phenomenon observed at extremely low temperatures, where a fluid can display effectively zero viscosity under special conditions. Viscosity connects the microscopic world of molecules to the visible world of flowing liquids and gases. It explains why syrup crawls while water rushes, why air creates drag, why blood flow depends on vessel size, and why machines need carefully chosen lubricants. It also reminds us that fluids are not passive substances. They resist, transfer momentum, dissipate energy, and sometimes change personality entirely depending on stress, time, and temperature. So the next time you watch cream swirl into coffee, paint spread on a wall, or oil warm inside an engine, you are seeing viscosity at work, the hidden internal friction that shapes almost every flow in the real world. If you found this helpful, please like this video and subscribe for more explainers.